Okay, very good.
Okay. So Francesco,
okay.
if you will, the floor is yours.
Thanks. Thank you so much. I'm very glad to be here in this context to present our research. Thank you very much to Johanna, to Julia, to all of you for the invitation, for being here with us. Okay, let's start. The main issue on which we focused all our research in the last 3 years is about thinking about how goal-directed behaviors in agents, in humans, in animals can be described. And we built out a framework, a theoretical framework, an hypothesis, which is both a functional hypothesis and an hypothesis about the neural substrates, and also we will see a computational hypothesis. Let's start from the main features we are searching to explain about goal-directed behavior. We just individuated with these 3 features. The one is being oriented toward future outcomes. The second one is being sensitive to failure or success in achieving one's the outcomes. And the third is being flexible in a situation which are in similar situation, and having different choices. For example, you can think about the situation in which you are in front of a door with a knob, and you have 2 different there is 2 different possibility of interaction between you and the knob of the door. You can use it for turning in one way, switching one way and opening the door, or turning in the other way and closing the door. The situation is the same, the context is the same, and you have to choose which one of the 2 interaction to go into with this part of the world. Okay, being oriented toward future outcomes means having a knowledge of these possible interactions, a knowledge of the relation between your actions and the outcomes, and having most of all the possibility to anticipate the outcome in your mind. Being sensitive to failure or success, means having the possibility to compute, to evaluate the matching between the actual situation and the situation in which you want to change the world. And about the third feature, being flexible, means, as in the example, being able to choose between different possibility of interaction, the one that you will fulfill, you will trigger, the way you will interact with the world. Most of the research about goal-directed behavior ends in theorizing the use of internal models in this process of interacting, of choosing the interactions. And in all different field of research, model-based theories, there is this conceptualization of having a model in which you simulate the world, in which you can define your desired state in the world, and you can find the way to change from the current state to a further state through a forward model. And you have your internal simulation of the world going on. And this internal simulation is made upon, they say, they all say, the use of an internal model in which the latent variables of your words of the words you're facing with are just defined. Then the distant information about objects, about relations, distances of objects in the words are just defined. Then there is a problem. There is a first problem in this kind of modelization. First of all, you should answer to these two questions. How do you learn this internal model? How do you build? How does an agent, a human or an animal, builds an internal model fulfilled of all this information about the outside world? And the other one is, where do internal states come from? How do you learn to have an internal representation of latent variables as distance, different objects, etc., etc. And another problem is that this way of thinking is based on prediction, or on modifying one's behavior based on using a prediction error. And all these models keep use of two kinds of prediction error. One is at the time of the current state of the agent. In the meanwhile, you're executing an action toward a goal, you can compare online the current observation, the current sensory observation, with an observation which you predict based on your forward model. In the same way, you can just have another error about your theoretical model and the way you correct it. And also, importantly, you have another kind of error, which is the error between your current inferred state within the model and the desired state within the model. Okay, this is the error of which we were talking about before when we said in a goal-directed behavior, you have to match your desired goal with your current situation. But here there is another problem. If you have this internal model, you have to run it. You run your simulation, going from your current state to your predicted desired state, and then you have to and then you can collect the error between these two states, the predicted desired state and the actual desired state. Okay, then it's something that it seems quite impossible, because at every single moment you have to run again the whole simulation to keep the online information about the error with your final goal. This one thing. And the other problem is that in this kind of models, it's very difficult to think about how the desired state can be anticipatory. There's a lot of literature that say that when we have a goal, we anticipate the final perceived state, quite as like we are feeling it. We are, it's like your perception is just like it's present to us. In that kind of models, you cannot reconcile the fact that you are predicting the current state, then your current observation, and the fact that you should also anticipate the desired observation. We are making up a different framework in trying to reconcile these problems. We are tackling the problem from another point of view, and we are building our topological alignment, as we call it, hypothesis, which eventually, hopefully, can allow us to describe this selection and goal setting and the use of the goal-directed behavior without prediction, without having internal models. And the core of our idea is having a multimodal internal space in which each point is anticipatory of both the effects and the actions. The internal space in this hypothesis would be a topological map of these action effect mappings. And in this internal space, the distance between the map perceptions and the map goals would be a measure of success, so that you feel the success when these maps are currently aligned. As I said, this hypothesis is both a functional hypothesis and it wants to be a neural hypothesis as well, and a computational hypothesis. So let's first talk about the functional part of the hypothesis, the core idea. This hypothesis came from the idea of the ideomotor principle, which goes back to William James, and the principle for which action can be triggered by the anticipation of an effect. This ideomotor principle was restated by Prince Hommel in a vision in which you have a common coding hypothesis, in which you have a shared representation system for both sensory events, perceptions, and action plans. Our hypothesis is a kind of common coding, but this common coding is defined in our way by the internal geometry of this space. Okay, then the main idea is that you have this internal common coding in which these mappings are structured, and the internal structure is topological, and it is a topological map of both perceptual and action components of the effects. But how can an agent build this topological map over a multimodal space, starting from, let's say, nothing, even though we know that no one starts from zero, from scratch. But let's try to build up a computational idea about how can this came from. And we start from the way a topological abstraction can be computed. There is in machine learnings and mathematics, there is a world fields. There is about dimensionality reduction for abstracting the informations, the information that usually are sensory information, from a high dimensional to a low dimensional domain. And a subfield of this is topological dimensionality reduction, in which you find this low dimensional space in which you maintain a topology. Let's say in this low dimensional space, similar items in the original space equals to closer mappings in the abstracted space. So that in this example, you have a data set of flowers, and they are mapped into a topological space, so that each point of his map represents a prototype of flower, which is slightly different to its nearby to the nearby prototype. This is the main idea, having this topology of abstraction. And let's start, and let's give an abstract example of how this topological abstraction can be used in our context. Let's define an abstract domain of geometry shapes, which vary with respect of two dimensions, sides, and the kind of shapes. Sides from bigger to smaller, and different shapes to square, from square to triangle. Then with the topological structure, we can map this perceptual information in a two-dimensional space, in which distance of one dimension informs about shape, and distance on the other dimensions inform about sides, and you can have difference on both dimensions. You can do the same on actions, not only on sensory information. Let's focus about more very abstractly on grasping. Let's say we have this simple gripper, robotic gripper, which has a very simple with 2 degrees of freedom. For sake of simplicity, we are here abstracting the action, the complete action movement with a posture, but it's only for the sake of this simple representation. Let's say we have different kind of grips. Some are precision grips, some are more open, and we have different angle of grasping with the wrist. And we can abstract information about these different actions in the same way on, for instance, on a 2D space, so that different grasping actions can be mapped on this internal space, and the closer the similar one, the more similar one will be near each other, the less similar will be far away one from another. If we have these two topological structure, we can think about aligning them so that at the end, each point defines both spaces, both original domains in both modalities. And then you can create a distributed multimodal mapping in which each point defines both a perceived event and the action to produce it. Then at the end, this point in this common space trigger the behavior and anticipate the multimodal perceptual effects of this behavior. I'm saying multimodal because you can have this alignment between multiple maps. Let's say you could have different sensory modalities mapped in the same way, and you could put them together, align all these mappings, so to have a multimodal mapping. This topological alignment hypothesis is about learning. It's about intrinsically motivated learning. This is because the main feature of this idea is that the internal distance between this mapping can be used as an intrinsic signal of the contingency between one's actions and actual events. Then minimize this distance means, from the point of view of the agents, minimize the error that there is between the anticipate perceived event and the real perceived event when you act when you trigger the action, of which the anticipated perceived event is an effect. So in this way, by minimizing this distance, you finally have aligned maps. This, as we said, this distance signal provides both a measure of success and a way to for the agent to say, okay, I reached my goal, I can reset my goal, I can go to something else. Okay, this was the core functional idea in a very rough way. And the features of this idea is that in this way, action can be accessed by their effect, the motor principle. There is the interaction between different sensory and action modalities into an internal common space. And by this way, an agent can generalize across a continuous space, which is the topological internal space, so that any point in this continuous space can become a different action effect pair, even though I didn't experience it directly, just by interpolating over this continuous space. What are the key assumptions of this proposal, this framework? One is that there should be a proto-organization of topological space internally to keep coordinate consistency. Even though points at a coordinate don't yet relate to original context. At the beginning, you have mappings, internal maps, which are meaningless because they are not attached to any action or sensory event, but eventually with learning, they get to be meaningful because you close the loop with, between in each point between your actions and effects, that perceived effects. Another assumption is that learning of those mapping should be interdependent. You cannot learn actions or information about perceived event separately. They must be learned together. And eventually this framework is able to achieve an explanation that meet the criteria for goal-directed behavior. In this framework, an agent is able to anticipate the action effect in the internal space that will be caused by acting. Then you can have orientedness toward an outcome. In the same way, you can measure the success because you can evaluate the alignment of sensory and action mappings in the internal space. And finally, you have a multimodal map of action effects, and you can endogenously select between them in the same context. Okay, this was our functional, the functional explanation of our idea. Let's talk about how this idea can be plausible on a narrow level. Let's say very briefly that, as we all know, topology is a constant feature of the whole brain in human beings and other animals. These are some examples. For example, at a topographic level, we have an organization of visual cortices which is retinotopic. Then each of the visual cortices, both V1 and the other more associative V2, V3, and V4 share an internal map of the retina, of how retinic receptors are disposed in the retina. One other example is the sensory motor organization of the motor cortex, in which you have different regions in the motor cortex with maps to different regions in the body. And the same, exactly the same happens, quite exactly, happens in the somatotopic organization of the somatosensory cortex. Then on the micro level, we also have topology. For instance, in a lot of topology, for instance, it is well known that in the visual cortex there are microstructures that we call columns. In each of these microstructures, you have information about the orientation of stimuli, the spatial orientation. Then you have a feature which is not about topography, but it's a feature of the shape of the object. which is mapped into a topology in each microstructure of the visual V1 cortex. At the same, in the same way, in the motor cortex, we find a microstructure, microorganization, which resembles a topology based on, for instance, in one part of the primary motor cortex, they find topology about the preferred direction of the arm and limb. Then there is a lot of, in the whole brain, there is a lot of structures which are topological and topographic. And then there are these seminal works about Graziano, in this work by Graziano and Alfalo. They showed up their findings in which they found that there is a topology of complex action maps in the premotor cortex. The different complex actions, for instance, reaching to grasp or defensive behavior, or climbing, or mouth to hand to mouth behaviors. Those are can be triggered by activating the motor cortex in the different regions which are in a topology, distributed within a topology. Incidentally, they used to model this development of the motor cortex with some computational model which are the same, which we will describe in a while. We also use. From that, there is another very seminal way of researching by Rizzolatti and Fadiga, Fogassi, and colleagues. They found that in the fronto-parietal system, in the region defined by part of the frontal cortex and the parietal cortex, there are a lot of neurons which are bimodal. There is region in the premotor cortex are also activated by somatosensory and visual stimulation. And on the other side, parietal neurons seems to encode motor acts as well as sensory information. And all these research ended in these studies by Kaz and Stepniewska. There, among others, found that in the frontoparietal system there are several action perception domains in which each parietal region is linked with a corresponding frontal motor premotor region, defining an action perception loop. For instance, you have a reaching domain, a defensive domain, a grasping domain, a nice domain for oculomotor vision. All these domains can be described within a topological alignment framework. So that in this hypothesis, you have all these regions which are different topologies, which are aligned in between them, so that you have a motor topology which is aligned with a sensory perception topology. And they found that this same structure stands for all the superior mammals and also for inferior mammals as well. And finally, there is nowadays a lot of evidence that in the fields of epigenetics, of the development of neurostructure, these two hypotheses, the radial unit hypothesis and the proto-type hypothesis, could be, or nowadays they are taken for almost for certain. Then, and those hypotheses are based on the fact that there is in the embryo, there is a region, a subcortical region, from which all cells migrate and develop, and they maintain an information about their initial position, close in which different groups are close to each other's. Then in this way, you maintain a topology and you build up the link between topology in the whole cortical plate. And this could be a key to an answer to how can a proto-organization be there, on which you then learn the alignment of different topologies. Okay, this was about the neural ideas, the neural hints that our hypothesis can be plausible. Let's now focus on the computational level. How can we build computation from the computational model based on this hypothesis? The main architecture to build this hypothesis is made of this two-couple system. You have two different mappings from sensory and from action layer to the internal layer. And these mappings can be used both forward from the sensory domain to the internal domain and backward from the internal domain to the sensory domain and the action domain. How can we build topological maps? We use a well-known neural network framework, the self-organizing maps, which are neural networks that allows you to build a map of prototypes of the sensory information. In this example, you see that you learn sorry. Okay. You learn this data set of images, for instance, which are animated, pre-processed and mated images, mated numbers. And this is a data set of various thousands of different images animated from real individuals. And eventually, the network learns different internal prototypes in this data set, but it is able to order these prototypes into the grid of its output units, so that each unit is more sensible, is triggered more than others to a different subset of items, and the similarity of items is recalled in the internal topological organization of the network. We also built up a variant of this self-organizing map, the supervised topological maps, in which you can decide from outside how this topology is distributed. The first idea, the original network is self-organizing, so that you don't know how this internal structure will be learned. For instance, you don't know if the ones will be in the bottom right corner or in another part of the region. There is a self-organization of these prototypes. You can constrain with this variant. You can constrain this internal organization, so that you constrain zeros to be in the, for instance, in the upper left region, and nines to be in the bottom right region, and so on. With this mechanism, we hopefully we are trying to implement the main idea of alignment between topologies, so that, for instance, one topologist can guide the organization of the other topology. For instance, and mainly in our models, the action topology, the topology on which the goal is chosen, also defines the anchor of the learning, of the current learning of the other topology, so that they learn together, and the subregions of the topology learn together and keep to be aligned. This, in all these networks, you can go from the input to the output activation, or you can go in the inverse way, from the triggering of an output unit to the generation of a new item. And this algorithm can be used in both ways: in a bottom-up way for sensory elicitation of the effect. In this case, you have a sensory information which activates the mapping of the effect, but this mapping is linked to in the same coordinate with the mapping of the action to be triggered, so that eventually this activation of the effect triggers the action, and you experience the anticipated effect. So that is your hand over the gripper over the object. And this kind of structure can be used also in a top-down way, so that you elicit an effect by eliciting a goal, which is an action, but it is also the anticipation of an effect. So that if you are faced in a situation in which two different sensory information, perceptual information is presented, your elicited goal biases one of the two, so that you finally go for the correct action, for a specific action, which will end in the final effect related to this internal mapping. This algorithm is, as we stated, an algorithm about learning. For this, you eventually need a predictor of the effectiveness. This predictor keeps information about those representations and learns to predict if an elicited representation of a goal can lead to success. That is, if there is a final alignment between your sensory representation and your actual representation. And this prediction that is about the current competence on that goal is used to learn both sensory and action maps in the interdependent way. So this competence signals both guide and modulate learning of sensory motor mappings and modulate the exploration of actions. You decide if you explore or exploit the actions without any further error based on your current competence on that. Okay, I will just show you two different scenarios in which we implemented this computational architecture. The first is about grasping. We built up a simple 2D dynamic environment in which there is an arm with a gripper, which is 5 degrees of freedom. There are 5 joints. And you can control how they are opened. This is the way you can control the robot. And you have 3 different sensory modality. The vision that is defined by the part of the space which is encompassed in this fovea. The touch, you have 40 touch sensor in the gripper, both in the internal region and in the external region. And the proprioception, that is the current position of the joints. As we said, the joint position are controlled by the system, and this information, this control is triggered by a simple neural network, and the action of this agent is defined by the current policy, that is, by the current weights of this network, so that the system maps the different weights, states in the different configurations of weights of the network in a state of the weights. The action domain in this context is this space of weights which defines the rules of behavior of the agent throughout the whole episode. By this way, we can align these 4 maps so that we have a map of actions which is aligned with a map of visual prototypes, and it is also aligned with a map of touch prototypes, way of the proprioception prototypes, the way the gripper joints are positioned, and a touch map, the way the gripper touches in the final the final touch effect. And these are some visualization of the dynamics of the internal mapping during 2 different episodes. You see that by this way, the system is able to having orientedness because each goal anticipate the prototype for the sensory effect. You can evaluate success because you can evaluate how these mappings get near to the goal mapping, to the one that is chosen at the beginning. And you have flexibilities because you have different sensory motor effect that you can trigger. Let's say in a situation in which you both have blue objects and red objects, you can trigger based on some other internal internal way. You can choose your goal between all of these effects. Another context, another scenario is about visual attention, how we voluntarily decide our saccading in our visual field. In this scenario, we'll build up a simulator in which you have a simpler eye in a 2D space. This eye is composed of a retina within which there is a fovea, the internal region. This is what you can see in the fovea. There is 16 by 16 pixels. And you also have a saliency preprocessing in the whole retina so that you can define a level of saliency for each pixel in your retina, which is based on boundaries, is based on Gabel filters. This model per se is a very abstracted but already a good model of a reactive movement based on bottom-up attention of our eyes. And it's a very high-level description of what's going on, for instance, in the computation in which the superior colliculus in mammals and in humans is involved. But we also added to this system an attentional filter, which is a filter which, depending on the point in this retina space which is chosen, which filters the saliency map so that you can look at saliency only in the subregion currently defined by this filter. By this way, you can convert this reactive behavior in a voluntary one, just deciding the part of the retina to which you will pay attention. For instance, in this case, you have this region so that you constrain to look at the most salient point, this angle, and so on, as far as these attentional filters changes. This is the way to transform a reactive saccading behavior in a voluntary saccading behavior, and this is what they are finding that is something that is happening, for instance, in the frontal eye field system, something like that, which is retinotopic and which is information that is very similar to this one. Okay, then this is our action in this case, and this is our perceived information. And then we can align these two domains, building two different maps, so that the agent finally has mappings in which each point is a point in which you have a proper attentional filter and the corresponding effect on your fovea that should be present if you succeed in that saccade. We also, in this model, we also added a further information, which is an information about conditions. That is about the perceived information which are acquired before you have the saccade. Then there are two maps. One map that maps the information after the saccade is made, the effect, and the other information is about the condition, the visual information before the saccade. And you can see in this simulation a case in which we learned mapping of red triangles and blue squares. Then you have two different regions of prototypes. And when you have a particular object, you, given this learning, you implement particular dynamics in switching from one effect to another, led by conditions. This that you see here is the map of attentional templates. Here, each point is a retinal position of a different attentional field, and the colors defines the position in the internal space, so that a red attentional filter here, it's linked to a red prototype here. And indeed, you see that these are features in which angles are pointed to the top, which is the current attentional filter here. Instead, here you have feature angles that are pointed to this region, and so on. And you can see here the different trajectory. This is the current one. The different trajectories that the system made when it's faced with different objects. Here we change the orientation, and there is a different trajectory here going on. And also with red triangles, you see there are different trajectory in the internal space. This is the internal space. This is this same space. And as far as you change the rotation of the object, you see that different trajectory are triggered. Okay, so that these dynamics of in the internal space represents dynamics of saccadic affordances, so that you have a chain of saccades, an effect that is triggered by a different object. And in the maps, you see that different shapes gets different part of the internal space. So this idea leads us to the idea that is more general than this one, that in general, these topological aligned domains can be used as blackboards for generative processes. You can have topological aligned maps of action effects here, and these and in which aligned sequences stand for events of complex sensorimotor interactions, and you can learn a memory of these trajectories, of these sequences, so that this memory can become a generative model. For instance, in the hippocampus, in the prefrontal cortex, it's speculative for now. And this model could use internal space, these internal spaces as a blackboard to memorize, recall, anticipate, and generate complex interaction with the world. It is different from the internal model as we stated from the beginning, because in this model, each memorized item is a sensorimotor event, a sensorimotor mappings, which is grounded with the word via this loop. This is memorized between my action and corresponding perceptual information. Then all sequences which are memorized are sequences or real sensorimotor effects in the world. And you can still generate sequences that are maybe quite different, even though there is there will be a constraint in the kind of sequences this generator will this model will generate at the end. And this is a way in which you can use this to trigger a sequence of sub-goal, a sequence of goal in the environment, and you can fulfill your goals even though there's no current context available.
Francesco, do you think it would be a good moment to stop, or in a couple of minutes? Because
yes, I'm quite finished.
I think the comments would be.
Yeah, you're right. I'm sorry, I went so long. Okay, just to say that we are implementing this in our current system with a recurrent neural network which is attached to the rest of the model, and it works as this generative memory. But okay, let's go to the conclusion. Okay, then to conclude, I'm sorry I went longer. We showed you this topological alignment hypothesis, in which an internal space is structured topologically and facilitate the aligned mapping between sensory and action states. This topology of the internal space is acquired via an intrinsic signal, which is related with this distance between proto representation. And we saw that parietal frontal action perception domain can be explained by this topological alignment hypothesis. And that topological alignment gives also a computational account of how an internal space can be built, so that can be used as a blackboard to anticipate and recall trajectory of action perception contingency events. In conclusion, topological alignment can be explained, in our view, goal-directed behavior, because it grants for these three features of anticipation, evaluations, and flexibility. Thank you. Thank you all for your listening, for your patience. Here, this is our groups, the two of us, Luca and me. There's also Andrea Mattera, which is helping us with the dynamical systems in the generative modeling, and Julian, that you know as well as us. Thank you all for your attention to your patients.